Shall we start the class, Bhutan?
Okay, sir.
Okay, good. Because I know that you just finished one session. Okay, very good afternoon to you all. And welcome to today. Lesson 8, Thermodynamics, 2020B2 Semester 2. All the three batches, manufacturing, mechatronics, and BST. And today's 5th February 2002, just after a day of the Independence Day. So, very hot and sunny time anyway. I hope you're okay to go with the class. So, balloons. So, blowing the balloon, I think we all can imagine this. We all can imagine this. Yeah, it is wonderful. Wonderful. Wonderful experience. It's very nice. And now, today, we will look into some little thermodynamic aspects in relation to this and extend this to the thermodynamics processes. Okay, so learning about the balloon in a different way. Okay, good. So when we blow the balloon, you can see the balloon expands. Means the balloon is here and there is a surrounding. So you can see that balloon displays its surrounding because balloon is occupying more and more of its surrounding. Means displacing environment. Example, balloon is displacing environment. So you can see here. Yeah, the balloon displaces its environment. Environment means occupying more space. More bigger, it takes more space of the surrounding. So, good to note this. Very good to note this. Displacing its environment. This can be an example. Let's see. Displacing environment. So you feel that when you blow this more and more, you feel we have to push the air harder because inside balloon, there is a pressure buildup and also there is a volume increase. Okay. And this volume comes from the blowing of air from the mouth. And more occupies, the pressure is building up and we have to apply a huge force. And there is a limitation. There is a limit for us to blow the balloon. Beyond that, the balloon explodes, so we have to stop blowing because it reaches our capacity. Okay. So, see, we are putting flow inside the balloon. Actually, it is something like a flow work because there is a flow we are putting into the balloon, but we are really putting an effort on that. It is not easy, especially for a little one. it is very tough to blow big because they work hard to blow the balloon, but they have the limitation. So really, there is a work done on the flow or air to make it flow into the balloon. So you should feel there is something like a flow work. So work on the flow or flow work is there to make the balloon enlarge, move and move, or blow, move and move. So this is basically now I'm going to change the shape of the balloon for our convenience of sketching. I take this shape for the balloon because it's easier for me. So see the balloon. So you blow more, it expands more, something like this. So I'm going to change the shape of the balloon. So let me take the same color. Yeah, little thick. Yes. Leave this aside. So this bow is blowing the balloon. This is the shape of the balloon. So initially, quite small. See, very small. Like this. Then small pressure, small volume, new shape of the balloon. Then putting more airflow into the balloon. A little bit. Yes, a little bit. Then blowing some more. Some more air comes in. So what happens is more bigger. Okay, let's say this 3D shape somehow. So I put this. So now it's like this. See, this boy may have the capacity to blow some more. Blew some. So originally, very small balloon, but now it's getting bigger and bigger. So you can see the surrounding, There is a surrounding. Obviously, you can notice it. This is the surround. This is the surround. So the balloon takes more and more of the surrounding or this environment. So this balloon displaces the environment. Let's see here. Now I take maybe at this time, okay, at this time. So let me take now just a tiny step of this. Yes, maybe balloon is already big in size, and there is a pressure and volume, the sizable pressure and volume PV. Okay, PV. So he's trying little more harder, and what happens is for little increase of volume, so this will be the volume increase, let's say delta V. So for this case, I will say let me make it more. Yeah. Okay. The volume becomes V plus little extra. Delta V. And if this delta V is very small, this P, and after making this balloon little bigger, let's say this P is the same and V change to delta V. So for this step of enlarging the balloon by delta V, okay, so work done to displace the environment by delta V, we can write the work done as W. Okay, that is delta W, because delta W is to make the volume increase by delta V. Delta W, we can write it as P times delta V. So keep this in mind. This is something standard. We can prove this. Always, when a work is done on the surrounding or on the environment, so we can see that the environment, the displacement, if this is delta V, or this is delta V, is the change in volume times the pressure, becomes the work done, delta W. So this balloon enlarging pushes the surrounding by delta W and find it way to look for the space for the balloon. Okay, so this delta W is something like done on the surrounding from the balloon, let's say. So quite interesting case. Delta W. Okay. From where this delta W came? Here. When you flow in some air, as a result, the balloon enlarges and it pushes the surrounding. Actually, this delta W is from the flow into the system. If this is a very slow blowing, okay, if this is a very slow blowing, this delta W is from here. Okay, this delta W comes from here. Sorry. See. So this boy flew in some air to the balloon. And this flow in comes with the work done on the flow. So this is something related to flow work. Okay. This is something related to flow work. Flow work. It's interesting. Flow work. Delta W. That is P times pressure times the volume change. So it's a little volume change. We consider there is no change in pressure, or the pressure change is negligible for this case. Somehow pressure times the displacing of its environment, or the volume increase or volume change, pressure times the volume change, P times delta V. Delta means change, V is volume. So this is this elemental work done. Okay, because of this flow expansion, air expansion in the balloon, but this comes from the flow work here. Okay, so always, if there is a flow make possible, there is a work component, or there is an energy component to make this flow possible. So this energy component comes to the flow from the mouth. but it's within the flow. So always there is an energy component related to this within the flow. Yeah. There's an energy component, yeah, to make the flow possible. So let me go for an example. Let me go for an example. Water tube and fire tube boilers. Anyway, I got this from the net. Let's say in a water tube, water comes here into the main manifold and then distributed into individual pipes running up and then all connected to a common manifold and leaves. That is steam. Okay. So even here, the fire tube, the fire is here. So the hot air passes through the tubes, all connects to a manifold and go for the stack, okay, or hot gas out. So let's say this is the situation. I think I will take here one by one. See if I take this. Let's say you can see the air flow through, the gas, hot gas flow through the pipe, flow through the pipe, flow through the pipes. Okay, so if I take one of these pipes, shall like this. And I will take the gas flow here. Yeah, I will take the gas flow here before that. The furnace. So hot air from the furnace. And finally, this goes to the manifold. Just for your imagination. So, it's easy for me to take from here rather than drawing. Also, you feel good. So rising the hot air. So two ends are here. So here in the middle, you can see the gas flow. How does this flow is at any moment? If you imagine there is a gas flow, continuous, but that's true. But at any moment, this is filled with gas, hot gas, but the gas here at the furnace end and at the stack end, different. So move from furnace end to stack end, this takes time. Okay, this is something like flowing of packets of hot gas or parcels of hot gas. Okay, flowing of parcels. Interesting. Let me try. Yeah, one parcel is here. So there is another parcel up front. I just keep a gap to show the difference. Okay. Another one. Interesting. So this takes place like this. Okay. Of course, temperature change. But I just show the same color because otherwise it takes more time to. Yes. Something like this. Finally. So this leaves like this. So here, there is no one to provide energy for this to push. There is no one here. Okay, actually there is someone. So if you imagine there is a person with this magical power. So blowing one over the other. Okay, these hot gas energy packets, one over the other, something like this. That's why the furnace effect. And anyway, with this arrangement, this all has some flow work potential. Okay, so there is a flow work within this. Now, I think this is interesting. Something like this. So otherwise, there is no way of moving this. There is an effect. Okay, let me take it here. I just put it. Yes. So if you take a special one here, okay, special one here, I can take any of this. I take the middle one. Middle one. Just this one. Maybe I will take line color, maybe this one. Yes. So this has to push the upstreams ones. Sorry, here downstream. No, this is the upstream. Okay, sorry, this is come from here downstream. So this has to push this and then go up. This has to push this, likewise. So for this surrounding is front and back, but this has to push the front. Okay, so even for this case, there is a potential. So if there is a pressure P, and volume V. So this should move from here. Of course, from here, this has to move to here to make the flow possible. So this will move from here to here. So that's how the moving is possible. It moves here. Likewise. So I'm not going to draw this. So flow work of this to replace this again, same like for the balloon example. I will put P delta V. I will change this to PV. Okay, so PV means at this pressure, at this way. If this needs to flow forward, so there should be a sort of energy PV other than the internal energy here. Of course, there is an internal energy of this. Sorry. U. Let's say if this is for unit mass. So later you can understand more. Other than this U, this flow work PV also here. There should be the flow work also to push this. So that is an additional one other than the internal energy, because internal energy is different. It doesn't help to flow this. But diffusion, yes, but flowing, no. So there is extra flow work related energy. So that is we put here as PV. U plus PV. So U plus PV. Internal energy plus flow work. So both the energy should be here, because without flow work, this energy, it won't move forward. So this total energy, internal energy is U. Flow work, we learned from the balloon example, P times, let's say V. V means for the 1 kg volume equivalent, let's say PV. If it is even, that can be delta, we don't worry. Yeah? So U plus PV. So flow work is PV. So try to understand a little bit on this. Same like this effect is there on the flow comes here. This effect is there when the flow is entering into this. Yeah. So this has that effect. So this pushes here. Same like this. So there is a built-in, there is an energy within for this flow. That is pressure times the displacement. How bigger the volume being displaced. So if this is V, the V should be displaced. So small v means this is 1 kg volume. Let's say small v, PV here. So this PV is the flow work. So this should be pushes this way PV. Okay, something like this. So he also almost P. Okay, here is almost P. P is the pressure surrounding. So we are going to replace this equivalent volume, this surrounding. Okay, so U plus PV somehow think about this. So this is internal energy plus flow work. This is what what's this flowing fluid contains, and this is we call enthalpy. Okay, this H is U plus PV. So H. So enthalpy is related to internal energy plus flow work. Interesting. So wherever you see some flows, so you can think about this two energy components. Definitely they are internal energy plus the flow work related energy, PV. So H is U plus PV in short. So H is PV is here. Internal energy component is here. So H is U plus P. So this is a very important thermodynamics parameter, or even we can call it as thermal property. Okay, that is U plus V. So wherever there is a flow of fluid other than the internal energy, there is another energy component here to move this forward. That is the flow work related energy. This does that flow work. Okay, good. So H equals U plus PV. So any applications, you can see this flow work.
Sir, please explain to me.
Sorry, Buddha.
U plus P into V, another P into V.
U plus P into V.
Yes, sir. And other than the P into V. What's the difference?
U plus P into V. So this P into V is the flow work. I explain here. Here example P times delta. It's a very small displacement. Let's say P times delta V. Okay. P times delta V here. So here flow work is pressure times this displacing in its environment. P times delta V. So always this relates to the displacing of environment. So here also this displace somehow when this moves, this equivalent volume V should be displaced here. Okay, something like that. So
Okay.
something like that. So if I take one more, they're very good that you are looking into this now. It is something like this effect is here. Of course, no one is there, but this effect is here. This effect is here. No one is there, but the fluid itself has this effect. Flowing, this flow push to the next. Then everywhere you can say this effect. This effect. So just imagine this effect. The flow work effect is there. Excuse me. This flow work effect is there. Flow work effect. Okay. Flow work effect is there. So from here, the parcel of hot gas pushes it. Same like what this did. Okay, what this does. The same like the pushes here. I think the best is, see, this being pushed here. This push, flow work. So then it pushes. So there is this effect. So no one to push this energy parcel. It has this flow work effect, otherwise it won't go here. This has again the flow work effect, otherwise it won't go here. This has its flow work effect, otherwise it won't go here. Again, same flow work effect of this moves this packet to the next place. After that, again, flow work effect. Okay, something like this, flow work effect. So this PV pressure is the same. Let's say this push V equivalent volume. So then P times V is the flow work done on this by the previous position. Flow work effect is here already, something like this. So think about this. Think about this, and flow work is this pressure times the displacing of surrounding. So for this, particular packet of hot gas moves to the next place. It is something like a flow work effect. Okay, moves to the next place. So this flow work is pressure times volume. So later we will see how we derive flow work as pressure times volume. But generally, when this nature of displacements of the surrounding, pressure times volume is the work done. Okay, pressure times the displacement. So we will talk about that afterward. But generally know that flow work is P times V or P times delta V if it's a very small work. P times delta V, little displacing of the surrounding. The pressure initially times the delta V. But here this case, the pressure times the same V displaced here. From here to here, the same V. You imagine like that. So then you have the energy because of the flow work also here, plus the internal energy. So that's other way. Yeah? So just imagine like this. So there is a better ways of understanding, but you can imagine like this. Enthalpy word. So always if there is a flow, the total energy is the internal energy plus the pressure times volume. Then I want to draw your attention to one more slide here. From the NASA website. So enthalpy. So I will highlight here the word define. So enthalpy is a defined property. Okay, state property means it's a property of this flowing fluid. Its enthalpy is the internal energy plus pressure times volume. See, V is the volume, P is the pressure, E is the internal energy. So you take note this. Because to make it easier, okay, to follow, even though we try to make the explanations, enthalpy doesn't give any explanation, but it mentioned as internal energy plus pressure times volume. Okay, that's how it is defined. Okay, defined means no matter we are justifying it, but you can look for the justifications. That is one thing, but there is a definition for the enthalpy means that is the internal energy plus pressure times volume. Okay, that is the point. Okay, so what is enthalpy? You know that is the internal energy plus pressure times volume. Okay. With this, again, extract from that about enthalpy is a property of a thermodynamic system. It defines as the sum of the system's internal energy and the products of pressure and volume. That means H is U times PV. Okay. H is U times PV. That's how it is defined. Then it says the pressure volume term PV expresses the work required to establish the system's physical dimension, which means to make room for it by displacing its environment. So this is the energy or the work required to displace the environment that should be with that flow or the parcel of that flow component. So this U plus PV, this displacement for this possibility, this may have that energy content. Okay. Actually, this energy content, I better put it. Sorry. Here. Okay, U plus PV. So the internal energy plus the flow work. Yeah. So this PV helps to move this from here to here. Something like that. Okay. I hope there may not be any misleading, because sometimes unnecessary explanations leading to misleadings. Okay, misleads, but I hope it's okay at this moment. So flow work, it is very interesting. Now imagine, this may have a better understanding. Let's say, displacing the environment. Let's say if there is a pinhole in the balloon. Okay. Today, entirely on the balloon example. So you flow in here, go out. Once this is, because you cannot blow fully if there is a pinhole. You cannot blow fully. So there is a limit. Okay, there is a limit. It is something like if there is a pinhole, see, only this, you cannot blow up to here. It's not possible. In, out, it stabilizes. See, steady, the same size, whatever blows in, steadily it goes out. So this is not possible. Okay, so open system. So there is some continuous flow. Okay, continuous flow. Take the flow work out. The continuous flow. Or let's say steady flow. Okay, steady flow. So it won't blow up to the fullest. Steady flow. Steady flow. Like this. See? In and out. Some more interesting. If you carefully look into that, you may see that. Yes. Out means again displacing the surrounding, because there is a surrounding being displaced. There is a surrounding being displaced. Surrounding is being displaced because there is an energy, surrounding air being displaced by this flow out. Flowing also has flowing. If I go flowing, see, in, out. Now little flow packet is coming. Yeah, like this. So see here, right side, you can see in, displacing all and comes out. Continuous flow. So this is, if there is a pinhole in the balloon, you can see this. So it's a nature of continuous or steady flow. You can see there's a packet or a parcel of air. Of course, the force is there. This moves and then finally it leaves. So every parcel moves, means there is force on this and there is a displacement. So there is a flow work always there. Flow work always there. So you can imagine this. Okay, you can imagine this. So it is very nice. So little more explanations. You feel good about this? Energized. When you push this, blow this energized packet of air makes this air displace possible. Finally, this leaves. Okay, so flow work, again, it's mentioned here. See, There's a pressure, you feel it, and there is a volume of air. So flow work is a function of pressure and volume, and it is pressure and volume. So because at pressure P, if you blow a volume equivalent to V, okay, at pressure P, if you blow volume equivalent to V, to blow that V volume of air at pressure P, the work done by your blowing from the mouth is P times V. That is flow work. Just remember that, okay? Remember that. So blowing of V volume here at pressure P, the work done here on the fluid is PV. This work done from the mouth, somehow we are getting some push, and then this PV work comes out, and this is on the flow work. So same way, in flow work is P in V in, out flow work is P out V out. So imagine if you blow V volume of air at pressure P, P times V is the work done by you on the fluid. So now this fluid does this work again here. So there is a similar, the flow work done from one parcel on the other. So there is something, pushing effect. So you can see same PV effect possible. But imagine in and out, the PV is done, PV is done, okay? So here, the total energy comes out. The total energy comes out. The internal energy plus the flow work of this. Because if not, PV energy component is here, this cannot disperse the surrounding. So before dispersing the surrounding, okay, or before displacing the surrounding, this must have this flow work energy potential as well, other than the internal energy. So after doing the flow work, this may have only U, but at this point it has U plus PV. Okay, good. So U plus PV out is here, so I just put it here. U plus PV out. So inlet also the same, you have certain U and the flow work P. In the middle also, a similar U plus PV is there because pressure volume is there wherever. And if there is a movement of this flow of air, PV effect is there. So U plus PV. Even in a stationary balloon, if you think of stationary balloon, now you can think of U plus PV because U is there, internal energy, PV also here. So even in the stationary balloon, means no pinholes, still you can have U plus PV. That's why finally it becomes a property. It becomes a thermodynamics property, a property of state. That's why. So it's finally become a definition, U plus PV. No matter it displays the surrounding or environment or not, still you can have U plus PV. Then it becomes a definition. A little more. Probably you feel much better. The balloon effect here. Actually, this is a power plant using geothermal energy from the ground. You inject water here. And return water is, of course, boiling. It's steam. So you take the steam, you run the turbine here. So inlet of steam, leaving the steam to condense, and the turbine turns and generates electricity. See, inlet, outlet, balloon effect. Blow in, leaves out. So it's a continuous flow. We call steady flow. You can see energized steam in, then energy released, but steam plus vapor may be out. Similar like a balloon, you know here. So displacing environment is a norm when there is a continuous flow. And if displacing environment is there, other than the internal energy, PV is there. So in and out. Quite interesting. It is very interesting here. See the turbine. So steam in, turbine turns, and the de-energized, this steam water, the two-phase mixture maybe, or even the little superheated or saturated steam comes down. So this makes possible because flowing of this fluid. If no fluid flow, it is not possible. Just turbine stay only, no turning effect. So this is the real scenario. The flow of working fluid comes in, goes out, turns the set of radial blades, and it turns the generator or the alternator. Yeah. So it is very interesting. This effect, this displacing, somehow you should feel good about this. The same balloon effect, we can see that. If you need one more example. Yeah, but anything? See, this is much better. The generator. Anything? The boiler. Again, the furnace here, energized steam comes in. And leaves the turbine. So you can see the same effect. So displacing in and out. Okay, it's very interesting. So we'll continue with these examples. So now you can imagine. It's very interesting, and even for this case, see the turbine effect here, the little boy blowing over the fan. It's the same, but only thing is turbine, it has a casing for effective flow of this working fluid. Even turbine can run without the casing, but not effective. Same like this, but it's the same phenomena. Okay, it's the same phenomena. So you should know this very well. So now further. Come back to steam afterward. See, flow work. There should be flow work in to push this the steam out, like blowing, you know, blowing, and then comes out. So there is a flow work in, P in, V in, flow work out, P out, V out. Of course, together with this flow work potential, there should be internal energy as well. So total energy level here is the internal energy plus the energy needed for the flow work. Even here, the internal energy plus the energy needed for the flow work, because flow work is needed to displace the surrounding, to find the way for this flow to go out. Otherwise, flow stops. You know, that's why. That's why energy in of the flow in, internal energy plus flow work in. Okay, so U plus PV in, energy in. See, steam. Steam must go out after work done, because if cannot go out, the flow stops. When the flow stops, no turning of the turbine. That's why energy out of the flow out, EO, is the internal energy plus the flow work out. That is U plus PV out equals H out. Later we will look into the units, don't worry. Now you know that other than the internal energy, there should be an energy component responsible for flow work. It is not the internal energy, but it's a different because of the pressure effect. Actually, who is blowing this to the turbine? Who is blowing this? Boiler. Yes, boiler is blowing that. Very interesting. See, boiler does this. Same like blowing from the mouth. Boiler does that part. So other than the U, the boiler is very high pressure. So when under high pressure, there is a potential for this flow movement because of the high boiler pressure. And also the lower condenser pressure. Condenser pressure is lower. They're both possible because of the boiler, because of the turbine and the pump here. The pressure difference is maintained and the boiler pressure is maintained because of this furnace delivered thermal energy here. Interesting. It's very interesting. So you should feel good about the flow work by now, and there is some familiarity. There is some familiarity. So you should think about this. That is very important. And finally, you came to know that U plus PV is something like a property. Even in the NASA website, it's defined because that's the best way to get it defined, because no matter it's for a flowing in and out or even stationary like this, U plus PV become a property. So if you go to steam table, so I take the 1 bar. See H. H denotes enthalpy. F means enthalpy of this water. Of course, saturated water and steam. The water enthalpy, the steam enthalpy, both at 99.6 degrees Celsius. So the H, the enthalpy, you can see. Hg, gas phase, higher energy, because that is Ug plus P times Vg. See, I did the calculation here. Pressure 1 bar is 100 kilopascal. Follow this. Pressure 1 bar means the 100,000 pascal means 100,000 Newton per meter squared, or this is 100 kilopascal. So pressure times Vg here, because we have to have appropriate units, take note. So pressure is 100 kilopascal times the volume in meter cube per kg, become 169.4. Pascal times the volume in meter cube per kg becomes kilojoule per kilogram. So this is P times Vg. Ug is this 2506 plus P times Vg 2506 plus 169.4 become 2675.4. What is this? 2675. What is 2675? This is Hg. So finally, this is being calculated as U plus PV. The concept is thermodynamically surfaced out. Finally, it becomes a definition, but it's calculated because P and V measurable, internal energy U also somehow measurable. U plus PV therefore can be calculated. Okay. So finally, enthalpy is taken from the calculations here. But enthalpy, even though you calculate, so this is the total energy, total thermal energy, somehow even can be defined as the enthalpy. So U plus PV. Because PV energy, flow energy also within the that parcel or packet of air. See, PV also within here. Okay, PV at the inlet, PV within here. That energy also a kind of thermal energy component other than U. Okay, so that's how that's been calculated. So this is the total energy of flowing fluid. Thermal energy, total thermal energy. Okay, that is part of that is the thermal energy. One part is the internal energy plus the other is the energy for the flow work. Think about this, Bhutan. Again, come to you. The same repeated slide. H defined in this way. Very interesting. H is U plus PV. Good. About U, internal energy is a temperature dependent. Okay. It's a temperature dependent energy. Temperature dependence means because of this kinetics, the particle movements, because of the temperature and these movements, there's a kinetic energy a lot because there are billions of particles together. It's a big amount if you consider 1 kg like unit mass. So this internal energy plus PV will be the enthalpy. It is quite interesting. So that is the system's internal energy. And I'm going to share a very great masterpiece of humans' innovations related to flow works. Okay. Yes. A great masterpiece. Let's see. Yeah, this one. You know this aircraft. We call this turbine engines. Aircraft turbine engines. Flow in, goes out. So there is a flow through this engine and exit. So the working fluid is the air flow in and passing through and leaving the exit. So H enthalpy is always there in consideration because the flow is being pushed, or that flow is replacing the preceding ones. Okay. Imagine this huge aircraft, size-wise very small turbine, engine turbine, aircraft turbine engine, very small ones. Two of these can fly this machine. See how wonderful the power packed within, quite compact and very reliable turbine engine. So very simple. Air goes in, leaves this, and somehow generates some power to fly this machine and also to power the internal, all the requirements, air conditioning, running the equipments and all. So power generation for the internal requirements as well as for the flight of huge massive. Okay, so this is a marvelous machine. Enthalpy plays a big role. That's why even these engines are being developed by these NASA-like institutions maybe. So for the propulsion technologies, enthalpy is a key. Enthalpy is a key. Because for them, enthalpy is more than definition, more than definition. For the developers, enthalpy is something pretty much alive. It is more than the letter U, or more than the letters P times V. So this enthalpy is a live effect. Okay, so that's why you should understand this live effect. Maybe it's difficult for you to explain it to others, but at least you should understand the liveness of these parameters, the internal energies, the enthalpies, the flow works, okay, the work done, everything. So that is what we call the true thermodynamics. It is not about the words. So if you need to look the reality of thermodynamics, this is a proof. Yes. This turbine engine generally like this. See, air sucks. This is the front side. Okay. Air sucks. Compress. Combustion. Power. Exhaust. Even for stroke engines, There's a suction stroke. There's a compression stroke. Combustion is not a stroke, but combustion is there in the combustion chamber. And power stroke. But in the IC engines, the piston cylinder, just simple two pieces, play around and make this four thermodynamic, this process is possible within two components, but in two cycles. But here, for suction or intake, separate component. That is part of the compression. So suction, then the compression separate component, combustion separate, power through the turbine separate, exhaust. Even at the exhaust, there is a nozzle component. Okay, good. Compression work, of course, suction, intake plus compression. So once you take this flow in and compress, the enthalpy rise from H1 to H2. Okay, there is an enthalpy rise from H1 to H2. So compression is H2 minus H1 compression work. In combustion, again, because it's a flow through, okay. So later you will know that combustion is H3 minus H2. Power out, work done from the turbine, H4 minus H3. Sorry, H3 minus H4. So change in enthalpies when the working fluid undergoes a series of thermodynamics processes represent the significance or the quantification of this work done or energy inputs directly related to the enthalpy differences when it give me a second, Buddha. Yeah, Buddha. So if it's very important to connect this. Okay. So this flow, steady flow nature, you can see in this turbine engines passing from one component to another, and the working fluid experiencing one process to another, finally makes this power and the propulsion possible. It's a wonderful machine. Okay. So here, the intake and compression is low temperature, low temperature. Even intake is minus when it's flying high, minus 40, even minus 60 maybe. But this is quite hot section. So you can see this. So no oil, no lubrication, but there are tolerances, but very reliable, somewhat precision machine. The reliability is the one that is very critical, because once airborne, so it is not possible to repair this in there. So until comes down, the reliability should be there. So reliability is the number one for this. Okay. So all the thermodynamics, you can see in this nature of applications, you can see this all the wonderful thermodynamics applications. So later we can connect our knowledge, our book knowledge to this. If you really look into your one-time note, okay, you will see everything there. Okay, you will see everything there. So it's wonderful. So this is the machine. I hope you can see this. Suction exhaust from the behind. Okay, go in, go out. So air in, air out. So actually this is fun. So again, air out goes to surrounding. From the surrounding again takes the air in. Okay, but surrounding is atmosphere, the upper levels. Okay, air out also very hot generally. Consider hot because then this air outs go to surrounding means there is an energy loss to the atmosphere, whether it's on the ground or in the air. Energy out is there. So that is the heat contained in this working fluid leaving this system. Okay. And energy in is purely atmospheric. So energy out has more energetic when compared to atmospheric. So the difference is the energy lost to the surrounding. Okay, this is well explained. And compressed. Same like in the diesel engines, even petrol engines, you have to compress it. One reason is the compression makes your machine smaller, compact. And the other point is compression makes the temperature rise of the working fluid or the air to the ignition point of the fuel, which means compressed air enters the combustion chamber, interact with the fuel, there is a huge energy coming out. So inside there is a huge fire. Because of the fire, this air turns into gas. That's why we call one-way gas turbines, and huge volumes, but in limited space. So the pressurized air turns the turbine. We call it expansion, and there is a work done. Okay, and there is a work done, and then air, after that air leaves the system. That is exhaust. So energy in, energy loss, compression work out of this turbine portion is taking back for compression, and there is a network done. So other than the network done for the thrust, there is a huge velocity component here, a kinetic energies for the propulsion. Later we will look into the nozzle effect, not today. See, this all related to steady flow components, and these are helpful for your one-time note understanding in a better way. Okay, that is for your better understanding. So you can connect this with applications. That is very important. So I have 8 minutes. So let's see if I further look into this. The same another schematics. Your turbine done the primary work, the total work done by turbine, and the part of the turbine work goes into turning the compression, and there is a net work. So W net out is W turbine, that is W expansion. Expansion takes here in the turbine. Minus W compression becomes W net. That is one thing. And because of the fuel, this compressed air, okay, because air from the ambient go through the compression process, high temperature compressed air interact with fuel. That is a huge fire. That makes possible for the turbine to run. And finally, exhaust gas comes out. So air goes in, gas comes out. So compression is air, expansion is gas. But we may say this as a gas turbine. But if you ask what's the working fluid, I would say working fluid is air. Because intake is air. The compression is air. Okay. So you can have this nature of schematic also for gas turbine engine cycle. And then hot gas comes out, cold air goes in. There is an energy difference. So the hot gas energy dispersed to ambient as energy loss. So if you need an energy balance, energy in combustion chamber, energy loss here to the ambient, or Q out is Q loss, is the W total, not to say W. Yeah, it's the W total somehow within the system. I think I have to review this. Don't worry about this W net. Q in minus Q out is somehow W. Okay. So efficiency is the network divided by the network is the effective work by the energy. Okay, good. Back to the same. Yeah. You can have energy balance. You can have energy balance again. Okay. So later in the next week, we will look into the energy balance of each and every component, but you can see energy in here, energy loss here, loss to the surrounding. Interesting. So many components here, flow components, the fans, the compressors, then two types of compressors. One is low pressure, another is high pressure. Combustion chambers, turbines may be high pressure and low pressures, and the nozzles. So later we will evaluate each and every component for energy point of view. Okay. So in terms of energy, we will look into the evaluations afterward. So there are compression, expansion, combustions, there are nozzles, and even some cases we have to learn into the diffusers as well. Steady flow systems, these are, we will study those in next week presentations. Next week, I don't think next week you may have a study leave, let's say, in the coming weeks. And stationary turbines, compression, combustion and turbine. In power generations, you can see this nature of applications. Even Yugadhanavi, you have the oil. Turning the gas turbine generates the energy for the country to power up. Even there is a possibility to run this with natural gas. So this is gas turbines, also stationary ones, you can see. Wonderful machines. And the working fluid flows through this and makes these functions possible. Actually, if you look into the elements, these are no big deals to understand. All elemental level constructions, you can see. So that's all for today, Bhutala. Just I did some, not to say rushing, but this is equivalent to a 4-hour session. So I did it in 2 hours. Okay. 4-hour session, did it in 2 hours because you have a capacity as B2 students. So try to understand this, and I can send you the one-time daily note to you so that you can go through this. Okay, you can go through this. It is quite interesting. See how to catch up this flow work, enthalpies, the internal energies, definitions of the enthalpies, steady flow systems, and some applications, power generations, even this aircraft turbine engines. Interesting. So that's all today. Later we will do some evaluations and analysis. So background preparation, enough for you to go through your notes. In the notes, you will see everything. Okay, Puta, any problem before winding up? Any problem? Yes. So, any questions, anything? Of course, there are many things for you to listen, for you to drill. And actually listening to the music and following thermodynamics, that is not compatible. It won't work because thermodynamics, also you have to see through the mind. That is very important. So you have to have a lot of imaginations. So learning thermodynamics, while learning, you cannot be multitasking. You have to think of this, you have to follow this, you have to inquire this while listening to the lessons. So listening to music and attending the other works, looking into thermodynamics is something not possible. Okay. So you have to take note of this. Somehow learn what enthalpy means. That is very important. And the flow systems, I think you can visualize this. You can imagine how simple these are. Okay. And phenomenally, as a turbine, you should see the flow of the working fluid passing through this. It is very important. Yeah. Okay. It is very important. Any questions, Bhutala? Today participation also looks that much. Any question? Any question before winding up? Any question? Any questions before winding up? So let me stop the class. Try to go through this. Okay. And I will send you this note as well. And try to understand this, what's practically and phenomenally taken place, and look into a one-time note and try to understand. It's quite easy for you to understand the one-time note, your text, so that you have something like a combined theoretical and its relation to the, or its connection to the practical aspects. Okay. So I'm going to stop the class now. You may be getting 2 weeks study leave for semester 1 exams, and let me check it and convey to you. So anyway, see you in the coming weeks. Bye, Putala. Take care, all of you.
Thank you, sir.
Thank you,
Thank you, sir.
This one, a better video is, I just uploaded a better video. Maybe I will upload this as well. So try to, somehow understanding is something totally personal. That's why. So we will try to feed you with better stuff for your understanding and imaginations, but it is your total responsibility to have some better understanding, to get some better utilization of this knowledge. Okay. Thanks, Putala. So let me stop the class. Bye. Bye.
Thank you, sir.